So yesterday, we started talking about the cell theory, okay? The points of the cell theory being that all organisms, not all things, all organisms are made up of cells. Things would include rocks and stuff like that that aren't made of cells. So make sure you always use the word organisms, okay? So all organisms are made of cells, okay? Also that the cell's job, all cells' jobs, are to carry out the basic functions of an organism. Process your food, burn your fuel, find ways to release that energy, okay? Get rid of waste products, all of those kind of things, all have to be done individually at a cellular level. Okay? And last point of the cell theory was that cells reproduce by essentially splitting in half. Okay? All cells come from the division of existing cells. Now, in order to see cells, which is what we're going to be doing on Wednesday of next week, okay, is to use a microscope. All right? Now, how many people have used a microscope before? Okay, good. So, our microscopes are pretty good, okay? They're still in pretty good condition for the most part. Some of them have had some electrical work done, but for the most part, they are all still in very good shape. So we do need to treat them very, very carefully, okay? That is, when you carry a microscope, okay, you carry it with two hands, right? That is, one hand on the arm and one hand on the base. Okay? We carry it with two hands, one hand on the base. Also, you probably will want to try and at least somehow cradle the cord. Okay? This one has had the original cord replaced already, so it has a nice light cord on it. The original cords are heavy. The original adapter plug is very heavy, and if you let them dangle, they can actually pull loose. That's why many of them have had to be replaced. So it's best if you can kind of cradle them with a couple of fingers. Okay? This upper part here is the arm. Not the neck. People call it the neck. It's not. Okay? It's not the neck. It's the arm. Okay? I know that seems like really anal, but it's the arm. Okay? So you carry it always with two hands because inevitably, okay, if you're carrying it with one hand, that's when somebody's going to come along and bump your funny bone. Okay? They're going to bump you right here, and what's your natural reaction when your funny bone gets hit? Open your hand. Okay? And then the microscope, $700 worth of it, crashes to the floor. Okay, so you hear the crashing sound, then you hear the angry yelling sound, then the thumping sound, then the ambulance sound, then beep, beep. Okay, so don't drop the microscope. Okay, we don't want to have any broken microscopes. Okay, yes, that escalated quickly, didn't it? Okay, yeah, so you want to be careful with these when you're carrying them. Now, okay, parts of the microscope. I'm never going to ask you to label a microscope diagram, just so you're aware. Okay, but so that you know, okay, what the parts are. Okay, you've got your ocular lens or eyepiece here on the top. Okay, this is the thing you look through. Right? It has inside, and this is always funny, but okay, it has inside like a pointer. So when you look through the microscope, there's this thing like this. It's supposed to be there. I've had people try to clean it off. It's like, Mr. Quitter, there's something wrong with my microscope. Oh, well, put it on my desk, go get another one. I look through it. There's nothing wrong with this. Mr. Quitter, there's something wrong with this one too. What? Well, there's something in there, and I can't get it off. No, it's the pointer. Okay? It tells you where the middle is, and generally you try and put your specimen on the end of that. Okay? It is created by having a small piece of wire that's just below the ocular lens that just sticks out in there, and it creates a shadow that looks like a pointer when you look through the microscope. So that's supposed to be there. It won't clean off. Okay? Other things will clean off. Okay? Like people's eyelashes, okay? Hair, things like that. You know, stuff falls off of people. Okay? Dandruff sometimes onto the lens. Am I grossing you out enough yet? Okay, all that stuff ends up on there, so you do have to periodically clean the ocular lens, and once in a while, but not very often, you have to clean these lenses as well. Okay, these are the objective lenses, the ones that are on the revolving nose piece. Okay, so they are color-coded, but they're also very easy to tell apart because they're all different lengths. Okay, the scanning power lens is the short one with the red band on it. Okay, this lens magnifies 4 times. The ocular lens another 10 for a total of 40 times magnification. Okay? You use the scanning power lens to do exactly what it sounds like. Scan. Okay? That is, look over as much of the slide as possible under a low magnification so that you can find the specimen you're looking for. Are you going to see very much detail? No. The important part of the scanning lens is to find the specimen you're looking for and then move it on the stage, okay, by turning these little dials here. Okay, so there's little dials that move the stage around, okay, and the slide, unlike the ones you had at Jump All 2, okay, fits into this little thing and clips into place. Okay, the ones you had at Jump All 2 did not have a movable stage, and you had to move the slide around, which is really inconvenient. Okay, it just doesn't work very well, so we want to avoid doing that. Okay, so we don't have to on these. These move the slide very smoothly, and you can really control the movements very well. So once you've found the specimen, move it on to the center. That is the end of the pointer I showed you a minute ago. The reason you want to move it on to the end of the pointer is because once you have it there, it will still be there when you move up in magnification. So on your scanning power lens, you see a very large area under very low magnification. When you move up to the low power lens, which is the medium length one with the yellow band on it, okay, it is greater magnification of a smaller area. So if you don't move the specimen to the center, so let's say this is the specimen I'm looking at, okay, so I found it on scanning power, then I switched lenses to the low power. Do I still see it? No, that's why you always want to move it onto the end of the pointer so it stays in the middle. Okay, and once you move up, it's going to be off the pointer a little bit. It does tend to, you know, the change in magnification changes what you see. Okay, then you'll move up to the high power lens. Once you've seen what you can see on the low power lens. Okay, and the high power lens does the same thing. It magnifies a much smaller area to a much greater degree, 400 times. Okay, so you can see lots and lots of detail on the high power lens. Now, with the scanning power lens and the low power lens, okay, you'll notice there's two sets of focusing knobs. Okay, there's this large one, which we call the coarse focus knob, and this one, which we call the fine focus knob. Look at how much the stage moves when I move this one. Okay. This thing moves the stage through a complete range of motion with less than a half a turn. Okay, so it moves the stage a lot. The fine focus knob hardly moves the stage at all. All right, so when you're on the scanning power lens, turning this, you could turn this and turn this and turn this and turn this and turn this, and it doesn't seem like it's really doing anything. Okay, so you'll use the coarse focus knob when you're on the scanning power lens, and maybe to an extent on the low power lens. Once you move up to the high power lens, which is what's in position right now, okay, you won't touch this anymore. For this reason. Look how close the stage gets to the lens. Okay, you can actually, with some of our slides, drive the slide into the lens and crack the slide and scratch the lens with this. It has a lot of torque. Okay, that means a lot of twisting power. Okay, so if you twist this, you could drive the stage up, smash the slide. Okay, so you always want to use the fine focus knob. The other reason is, if you're using this on high power, you'll notice that you go right past focus so fast that you can't stop in time. Okay, so you want to use the fine focus knob. It'll make your life a lot easier. Okay. The other thing with the high power lens and the fine focus knob is that even though the things we're looking at are very small, they're still three-dimensional. They still have depth. And when you're on the high power lens, you'll notice for some of the specimens that you can't get the whole thing in focus at one time. It seems like you're focused on part of it and the rest of it is out of focus. And that's exactly what it is. It's like if I'm looking at Aiden right now, Sam is out of focus, right? My eyes can't focus on two things at once. Now I'm looking at Sam, Aiden's out of focus, okay? That's what you're doing with the high power lens with kind of bigger specimens, is you're focusing on one part of it at a time. So to get a full picture of it, you kind of have to look at part of it and then just kind of slowly turn the fine focus knob through the whole specimen to get an idea. Everybody follow me there? Okay. So we carry them with two hands. They're always returned with the scanning power lens in place for two reasons. That's the one that the next person is going to want to use first, and it's just polite to return it that way. Okay. And secondly, people assume that's the lens that they're returned with, and they grab the coarse focus knob and start cranking away, sometimes without checking which knob is in, or which lens is in place, and they might break a slide or damage something inadvertently. Okay. When you're using the microscope, always start with the scanning power lens. if you try and find something with the high power lens, but just sticking a slide in there and looking with the high power lens, it would be the equivalent of trying to find a single person in a football stadium with a telescope. Okay? Trying to find one individual person looking through a telescope at a football stadium. Okay? It would be, you would scan and scan and scan forever to find that individual person. Okay? If you're looking for a person, let's say on the other side of a football game, okay, you would say, you might know they're wearing like a bright yellow shirt. So I kind of scan the whole area like this and go, okay, I got a bright yellow shirt. Hand me the binoculars. I think that's them. Hand me the telescope. Now I got the idea. Okay, I don't go looking for them with the telescope right off the bat. Okay, because then I have to check each individual face one at a time, as opposed to scanning the whole side and looking for a certain trait that I might find easily. Okay, all right, cleaning. There is special paper for cleaning the microscope lens. Okay, if you wear glasses, you don't like grab a Kleenex to clean your glasses with. Okay, because it'll leave lint and stuff all over your glasses. Or you don't generally do kind of what I do, which is use my shirt to clean my glasses, because you never know what's on your shirt. Okay, and that's why my lenses on my glasses are all scratched. Okay, you get tiny pieces of grit and stuff like that in your clothes and on your fingers, and if you rub that against glass, sometimes that stuff is hard enough that it'll scratch glass. All right, so I don't want to see anybody doing this, okay, to clean the lens, because that's just gross. Okay, people put their eyes there. We don't want to get like pink eye or something. That's disgusting. Okay, so don't lick your finger and clean the lens. Okay, don't take your shirt and clean the lens. Okay, don't go. Like, it's just that stuff isn't going to work. Just take a piece of lens paper, and I'll have it on the front table. Okay, clean it with one spot. Okay, and then throw that piece of lens paper away. Don't use it again, because whatever it picks up, you don't want to be cleaning another lens with that. All right. Okay, most of the time, the lens you're going to need to clean is this first one, because it's closest to people's faces. They bump it sometimes, and get your oils from your skin and stuff. So it does need to get cleaned periodically. Suggestions for having the best viewing experience through the microscope. Okay, if you wear, what's the stuff that makes your eyelashes look bigger? Mascara. Okay, sorry, I'm a guy, I don't know these things. If you wear that, your eyelashes look bigger, and they'll look bigger when you're trying to look through the microscope. Okay, if you have really thick eyelashes, they tend to be kind of cumbersome, and they get in the way when you're trying to look. Every time you blink, you see them, because they kind of reflect off of this lens, and the lens's reflection is enlarged. So they get distracting and hard to see with. So you might want to not wear that when we're looking through the microscope. Okay, the other reason we don't want you to wear that is because it falls off in like small bits of clumps and dust, and it gets on the lenses, and then they require more cleaning. Okay, because if your eyelashes are really long and you're looking through, they're brushing against the lens all the time. Okay, so it's best to not wear mascara on days when we're using the microscopes. Okay, another thing is, at least for me, I find it's easier to use the microscope when I'm wearing my contacts as opposed to wearing my glasses. Okay, because I find I'm always hitting my glasses on the microscope. Okay, when I'm wearing them, because I'm trying to get just a little bit closer. Okay, and I just find it's easier if I'm wearing my contacts. So if you have both, okay, it's a good idea to probably wear your contacts on the day when we're doing a microscope lab. If you only have glasses, obviously wear your glasses. Other things. Make sure that you turn the light on. I had groups in the past who have just tried to do this lab without the light on, and it's really difficult because it's dark. Okay, the light switch is right here at the back, so plug it in and flick it on. Okay, and the light comes on. You can adjust the brightness of the light. There's a rheostat right here on the side. Okay, like a dimmer. Okay, so you can just rotate it and change the brightness of the light. And another thing you can do underneath, okay, there is this little condenser diaphragm. Okay, so there's a lens that condenses the light from the light source and focuses it through the specimen. Okay, and adjusting this changes the amount of light that's allowed through. Okay, it's kind of like the shutter on a camera. Okay, and so you can change how much it opens, and sometimes that helps to see things that are really, really not colorful or not dyed or things like that. It increases the contrast. That's the difference between light and dark, and sometimes it just makes something jump out, okay, by changing that a little bit. So those are adjustments you can make while you're looking through it to change how things look and maybe improve how they look. All right, yeah, that should be it. one other thing. When you are looking through this and you're sharing it with a partner, okay, I always see people do this and they're moving the microscope around on the table, okay? And when you do that, especially on the lab tables, because they're made of a different material, they're sticky and it kind of chatters across the table. As soon as you do that, you've knocked it out of focus, okay? The top moves. So we have one partner look through it and then just turn the ocular lens towards the other partner and it'll stay in focus a lot better, okay? And you won't lose it in between. Okay. All right. So parts of the microscope, okay, we kind of talked about those, okay, we got you're not going to be asked to label this as I said before. You've got your eyepiece or ocular lens, the eyepiece tube, okay, you got your arm here, notice it's labeled arm, not neck, okay. The safety rack, we don't have safety rack, we actually have the actual closing clip, spring-loaded closing clip, okay. Tension adjustment, you're not going to adjust that at all, okay. The coarse focus knob, the fine focus knob, on-off switch on ours is on the back, okay. It's got rubber feet to keep it from sliding around. This whole bottom part is the base, light source, condenser lens is on the bottom here, okay, all that kind of stuff. Okay. These are things you're going to want to make note of because they're not in your notes, okay. For our microscopes, our scanning power lens has a field of view of 4,000 micrometers. That means the circle that you see when you look through the microscope with the scanning power lens in place is 4 millimeters across. Okay? If you stuck a ruler underneath there, you'd see 4 millimeters of the ruler. Why is it important for us to know that, you might ask? It is important for you to know that because when you make your lab drawings or lab diagrams, because they won't be drawings, you'll be asked to estimate the size of the things you are viewing through the microscope. So if I'm looking at something on the scanning power lens and it takes up 1/4 of what I can see, how big is it? Okay, or 1,000 micrometers, 1 millimeter or 1,000 micrometers. Okay, does everyone follow how I did that? Okay, and it doesn't have to be exact. You don't have to do the calculations on the calculator. You just estimate. Okay, give me an estimate of how big it is by essentially how much of the field of view does it take up. Okay, that's how we estimate the size of objects. All right, so our scanning power lens magnifies a total of 40 times and has 4,000 micrometers worth of viewing area. Okay, on the low power lens, it's 1,600 micrometers, so about 1.5 millimeters. And it is magnified 100 times. Okay, and for our high power lens, 400 micrometers across. Okay, so the entire field of view on the high power lens is less than 0.5 millimeter. Okay, 400 micrometers across. Okay, and it magnifies 400 times. Okay, so a micrometer is 10 to the -6 meters. Okay, it is very, very small. So if I want to, again, if I want to estimate the size of something, okay, on the scanning and low power, you can kind of just go, well, it takes up about 1/4, okay? But when we're looking at things on the high power lens, some of them may still be very, very small, okay? You may have to estimate how many you think would fit across the field of view, and then divide the field of view by that number, okay? So if I say, I think 20 things would fit across, 20 of these little bacteria I'm looking at would fit across this 400 meters, I'd go 400 over 20 and find that each one is 20. Yeah. Oh, does it? But it doesn't have the picture. It's one calculation though, isn't it? Oh, perfect. Okay, so it was in your notes. Sorry, I forgot to put it in there. I must have just added that last year. Okay, so that's what we would see when we look through, okay, our microscope at various magnifications. Oh yeah, it's right here. Okay, that was my drawing to make it better. Did I make it better with the drawing? Probably not. Okay, now estimating the size of the object. Okay, you can estimate how many objects would fit across the field of view and divide the field of view by that number. Okay, you can do that if it's a really large number, but you know, if you can see that it's roughly a quarter or roughly a third, just divide it by 3, right? And you're good. Okay. All right. Now we got till 9:25. Okay. I'm just going to skip those questions for now. Okay, when we're drawing a proper lab drawing, okay, technology has come a long way since I was in university and we had to actually do drawings, which I hated because I have no artistic ability whatsoever. Okay, technology's better, so we don't do them the way I did in university because, well, it sucked. Okay, and we want to do it better. Okay, we have way better camera technology. So what we're going to do is when we're looking through the microscope and we've got something focused, we're going to put our phone up to there and we're going to snap a picture of it. Okay? And then we're going to label that picture in Google Drawings. Okay? We'll make a whole lab drawing or lab diagram on Google Drawings and then we'll insert it into our lab report as our lab diagram. Okay? It's just easier to do, and it's giving people a much better impression of what you actually saw because it's actually a picture of what you saw and not your like bastardized drawing of it, and that's just awful. Okay, I am going to show you how to do that today. Actually, that was my plan. All right, so this is what a lab drawing has to have on it. Okay, in the top right-hand corner of a lab drawing is your name and the date. Okay, so your name and the date always go in the top right-hand corner of a lab drawing. There's just some format things that like universities are really incredibly anal about. Okay, and one of them is format of lab drawings. So name and date, top right corner. Then you have your specimen. And the specimen you tend to put to one side a little bit so that all your labels can be to the other side. Notice that on this drawing there are no labels going to this side. Okay? No labels on the left. They all are horizontal lines to the right. Okay? Because it makes it neater and more presentable and easier to read. There's nothing worse than a lab drawing that has a specimen in it that just goes everywhere. Okay? It's just haphazard, it looks sloppy. Okay? So we don't generally do our labels that way. Now, one problem you might run into with these straight horizontal lines is that maybe you also have to label this structure right here. Well, you can't really make another horizontal line right across because you'll run into uterus. Okay? So what you do is you go diagonally up and over so you give yourself enough room. Okay? Always ends in a horizontal line. Okay, and then below the drawing is the title. I know that's really counterintuitive. Okay? Titles always go at the top, except on lab drawings where they go underneath. Okay? So this is a cestoda, which is a type of flatworm. Okay? And it is looked at or is viewed under 50 times magnification. So we list the magnification. So for you, that'll either be 40, 100, or 400. All right? You actually list the number. And then give me the approximate size of the specimen, okay, by estimating the size like I told you before. Yes, good question. Which dimension do you do the size estimate? Always the longest dimension. Okay, this thing is not 50 across this way. It's 50 on the longest axis you viewed. All right, so how do we do this on Google Drawings? Unfortunately, I couldn't get the Chromebooks for today, so you're just going to have to watch me do it. Okay, so you when you go into Google Chrome, go into Apps, go into Drive, okay, and you're going to click on New up here, okay, in your Drive. And it's going to give you Docs, Sheets, Slides, and More. If you go into More, Google Drawings is in More. Okay. All right, so now I have an untitled drawing. Okay, I'm just going to insert into that drawing, if it ever fully loads. There we go. Okay. We'll have already taken a picture of this with our camera. Okay, and then what you have to do is make sure that that photo goes into your Google Drive. Okay, if you have the Google Drive app on your phone, which incidentally you should put on there before Wednesday. Okay, have the Google Drive app on your phone, then click on Google Photos, and it'll automatically copy anything in your camera roll into Google Photos, and that's in your drive. Okay, so I'm going to insert a picture or image here from my drive, and it'll ask you, do you need to take a snapshot, which you probably won't do. Okay, your albums, Google Drive, etc. So what I'm going to do here is go from my drive, so Google Drive, pictures. Okay, here's my picture of an amoeba that I took. All right, so I'm going to put that one in there. Well, of course, the internet's going to be really slow today. There we go. All right, so now I've got my amoeba in my drawing. I can move it wherever I want, and I can skew it, okay, if I want to do that. Because it's an amoeba, nobody will know, because amoebas are all different. Okay, no two amoebas look the same, so you can skew it a little bit if you need to. Okay, and then I'm just going to start putting lines off from structures that I think need to be labeled. So I'm taking this line tool up here and drawing lines off to the side, horizontal lines, okay, for things that I'm going to label. Okay, everybody with me so far? Okay, now I'm going to use the text box tool to put my labels on. Right, so I click on text box, and then you just bring the cross over, draw a box, okay, and put in there the name of the thing that you are labeling. Okay, so cytoplasm, okay, text box for this one. This will be the nucleus, okay, and then text box down here for this one. This will be vacuole. Okay, so now I've essentially got my labeled drawing, and of course if I find that anything's not kind of where I want it to be, I can always just adjust its position. Okay, when I want to put my name and the date, I can do the same thing with a text box up here, okay, and down below, okay, I would use the text box to do my magnification. Okay, so I would say 400, or sorry, this would be amoeba first, title first. Okay, amoeba, and then 400 times, and the approximate size of an amoeba is somewhere around 350 micrometers. Okay, and then I'm good. All right, I would obviously do the same thing up here for my name and the date. I'm just trying to get it done here. So now what I want to do is I want to download this. Okay, Google Drawings don't insert into anything. You have to turn them into an image file, like a JPEG or a PNG file or whatever. Okay, so I'm going to download it here, okay, as a JPEG image, because that takes up way less disk space and it'll be good enough for what we need to do. All right, so I've got Untitled Drawing JPEG. I would probably title it before you did what I just did, like call it Amoeba Lab Drawing or something that makes more sense than Untitled Drawing. Okay, and then I always make sure that it gets in the folder where I can find it again. Like you would want to put it in your classroom folder, in the science folder. Okay. So what I'm going to do is just put it on my desktop so it's easy to find. All right. Okay, so now that I've done that, I'm going to close this up, and I'm going to insert it into my lab report. We'll just imagine that this Google Doc is my lab report. Okay, if it was your lab report, you'd already have the template there. Okay, so now I just go insert image, okay, and take it out of my boom, done. Okay, got a labeled lab drawing in your Google Doc. Okay, you can move it around as need be, but they should generally take up a page. Okay, your lab drawing should be big enough that it takes up a whole page. If you are handing in lab drawings on your lab report like that, that's not very useful to me. I mean, yes, I'm going to be looking at them electronically, and I could just as easily do this, but I don't want to. Okay, make them big so I don't have to do that. Okay, everybody follow how that works? Okay, so that's all recorded. I'm going to include that. Every time we have a lab where you have to do a lab drawing, this podcast will be on there so you can just watch it again if you need the instructions again on how to do the lab drawings. Okay? Making sense? All right. So on Wednesday, we're going to be in the lab. Okay. First, we'll get all the pre-lab stuff done in here. We'll have the Chromebooks, and we'll get as much done as we can. Then we'll go across to the lab, and we're going to be looking at the letter E. Okay. I know that's not terribly exciting, but we need something that we know how it's supposed to be oriented. Okay. So we can see what the microscope does to it when we look through the microscope. Incidentally, yesterday, I think I forgot to show you guys this, but when Hook was using his first microscope and he was doing his experiment with lenses, okay, if you're looking at something small, light comes from that object and it gets to the lens. And when it gets to the lens alters the path of the light. Okay? And what it does is it makes it diverge if you have the right kind of lens. Okay? So now, this light down here is the light that came from the top of the specimen. The light up here is the light that came from the bottom of the specimen. So now I have this specimen greatly enlarged, but upside down. Okay? It's what we call a real image, okay? Because it's been flipped, okay, by the lenses bending the light. Okay? All right. Now you guys can try those questions. I wanted to make sure I got through the lab drawing thing before we did those. So answer those, okay, and then we'll hopefully have a chance to go through them. Okay, so real quick here, guys. We reviewed these at the beginning of the class. Okay, 3 points of the cell theory. All organisms are made of cells. Cells carry out basic functions. Cells come from the division of existing cells. Okay, 4 people considered to be the most important: Hook, Leeuwenhoek, and Schleiden and Schwann. Okay, and plants and animals have similar cellular structures and processes. That's why we think they may be related. Have a good Thanksgiving weekend. Eat lots and lots of turkey, or whatever it is you eat on Thanksgiving.